Moving on to the second lecture covering rotations, and we're going to use some of the stuff we learned last time to solve some problems. The first kind of problem is what's called a static equilibrium problem, sometimes referred to as either a static or an equilibrium problem. And an object is said to be in static equilibrium if all the forces and torques acting on it add up to zero. So here would be our equations if you assume a two-dimensional system, which is pretty much what we'll handle for these. So we're going to use these equations and show how we can solve for just about anything we need to in a static equilibrium system. Now, one thing real quick, and this is just, some people are different about this, but this equation, the sum of the forces equal to zero. Well, if you assume that the forces break down into two types, which would be positive or negative forces, then another way to write this is just to say that the positive forces equal the negative forces. This is how I think it's, I like to do it. And so instead of writing an equation like this, I'll write F positive equals F negative, and the same with the torques. Now, with static equilibrium problems, the object that you're talking about is generally not moving. It's in equilibrium. And so what happens is you need to pick an axis of rotation, because we always need to have a pivot point to measure our torque from. Now here you can pick any point you want, all right? And this is kind of confusing because it's not rotating, so what does it even mean, axis of rotation? Well, it's a point where you can basically use as a reference point for your torques. And the idea is that any point you pick, the torques about that point should sum to zero. If they don't, then the object would start rotating about that point. And so it's handy because you can pick your point to be someplace where there are forces acting. And if there are forces acting at that point, the moment arm for that force would be zero. And so therefore, any force acting at your axis of rotation can apply no torques. You can use this as a rule to save yourself some work. And the final thing before we solve some problems is this concept of center of gravity. So for a rigid body, all right, some, like they have a little picture of a beam here, all right, for a rigid body, the center of gravity is the point at which the weight is considered to act. Now, for objects that are symmetric and have their weight distributed equally, the center of gravity is at the center of the object. And actually this here should be R-A-R-E, the center of the object. And so right here, and now it's kind of tricky, but you can think of all of the mass as acting at this point right here, okay? And that'll simplify things and make things much easier, but it is a little bit tricky when you first get started thinking about that. And here's the steps from the textbook solving a static equilibrium problem. So first of all, they say model the object as a simple shape and draw a pictorial representation, and that's basically making our free body diagram. And then the tricky part, I think, the most important part, is picking the pivot point. This can save you a lot of time. Once you pick the pivot point, okay, you can go through and apply your Newton's second law version equations. And again, for me, I would do this as the positive forces equal the negative forces in the x direction, another one for the y direction, and then the torque positives equal to torque negative. So you end up having, in general, 3 equations for your system. So here's our first example, and here we have a bridge with 2 supports that has a dump truck parked on it. And the idea here is you want to find what the supports are, FA and FB. So, you know, if you were an engineer or something, you might want to find out what those supports, how much force they'll have to hold in order to do something like this. So our first step is to draw our free body diagram. We've modeled the bridge as our simple system. And so what are the forces acting on this system? Well, there's mg of the bridge. Mg of the bridge, which acts at the center of gravity of the bridge, which is just in the center of the bridge because it's a regulation bridge. There's mg of the truck. Now the truck technically applies a normal force down on this bridge, but that normal force will be the same as the force of gravity acting on that truck. And so mg of the truck down. And then we have 2 forces, I'll call them FA and FB, pushing up at those support systems. And so if we get rid of just the picture, make it a little less cluttered, here's our picture. And so the first thing I like to do is apply this force positive equals force negative. And of course this would be in our y direction. And for us, it's pretty simple. It's the two forces up, FA plus FB, have to equal the two forces down. Okay, and this has to be true. Unfortunately, it doesn't really help us much because we know that FA and FB don't have to be the same. And so it's a nice equation, but at this point we can't do anything with it. So next is to move to what's probably the trickiest part about this, which is doing this torque stuff. Okay, again, it's always a little bit trickier, this new rotation business. Now I'm going to make the axis over here, this red dot that I'm coloring in blue, where F of A is acting. And so you tell me what is the correct torque positive equals torque negative equation. All right, hopefully you got C. First thing is we know that, so again, it's kind of hard, but you got to visualize that this beam can be rotating, okay, about this point here. And if you think about that, F of A can't make it rotate, all right? So any force that's acting at the pivot point cannot be applying a torque. And so D, E, and B right away are gone, and so it had to be either A or C. And then what you do is you think, okay, which ones are the positive? Well, the positive torque was FB. FB wants to make this beam rotate in the counterclockwise direction, which is the positive direction. And so what you do then is you'd find the moment arm for FB. And if you look in this system here, this distance should have been 170 meters. The two other forces, the mg's, want to make it rotate in the clockwise direction, which is technically our negative. And then if you'd find the distances for those two guys, the distance from here to here, I believe, was 85 meters, and the distance from the pivot point to mg of the truck was 135 meters. Right over here. And so that leads us to equation C. And here's just me writing this out again. Now, at this point, this is just algebra, and so the hard part is over in a sense. You can go through and solve for F of B, and I got 8.8 times 10 to the 4 newtons. Now you can solve FA by doing a similar torque equation over again, or you can just take that equation we had before. Now we know FB, so there's only one unknown. I can solve this for FA, and I get 5.9 times 10 to the 4 newtons. So that's a pretty standard static problem. Let's give you one to try. So here I have a uniform beam of length 3 meters and mass 90 kilograms, and it's supported by 2 ropes as shown below, and it's in static equilibrium. What is the tension in the left rope? So go through and try to figure out this one. All right, so the first step I would do, well, first of all, the answer is A. Hopefully that's what you got. I would draw a free body diagram. So here I'll call this the force of the left rope, the force of the right rope. So there's those 2 ropes, and then there's the mg acting what's going to be at the center of gravity of the beam. And so we want to find the force of the left rope. And so it saves us a lot of time if I make the axis, okay, the axis of rotation over here where the right one is acting. So it's not going to be in the problem at all. And so I can set up my positive torques equal my negative torques. Now technically the positive torque would be caused by the mg. So it would be mg, and my moment arm would be this distance right here, which if you figure this out is 0.5 meters. How do I know that? Well, I know that the distance to where the gravity is acting is 1.5 meters. It's half of the 3 meters. And so this is a half of a meter in here. And then the negative force would be the F of L. F of L tends to rotate this thing here in the clockwise direction, which is negative. And the moment arm for that guy will be 2 meters. And when you have that equation, if you solve for that, you get F of L is equal to what? mg times 1/2 m divided by 2. And you get the 221. All right, so now that's static equilibrium problems. We'll do more examples in class, but what about dynamic problems, problems that are not in equilibrium? Well, what we can do here is, like we've said with rotations, every step of the way there's been a rotational equivalent of what we used before. So here would be our F equals ma equation. And so here we got this guy is sort of holding on to this airplane. The airplane propeller has a force of the thrust from the airplane, and it's rotating around in a circle here. And so we can think about this motion in two ways. One way is F equals ma, but then if we take some of our rotational equations, we can kind of massage this a little bit. And so if we assume that now that's a torque, so we're thinking about this as a rotational motion, it would be the force of the thrust times r. Okay, and so I can solve that and plug that in there, and then the tangential acceleration would be r times alpha. If I combine all of this, I get a new equation here, which is torque equals mr squared times alpha. And mr squared, of course, is just the moment of inertia. And so here, when we're all said and done, we get what is the rotational version of Newton's second law. And again, it kind of follows suit. Okay, so we have the force. Here we have our rotational force, which is torque. We have acceleration. Now we have our rotational acceleration, angular acceleration, and then mass is the connecting factor. And here the moment of inertia is the connecting factor. That plays the role of mass in rotations. And so what happens is if I was to solve for alpha, alpha would equal the net torque divided by I. And so I is what resists the angular acceleration. Torque is what's causing it. All right. Now we can apply this equation very similar to how we did F equals ma, but of course with rotations everything's a little bit trickier. But it's the same idea. An unbalanced net torque will result in an angular acceleration. And before it was unbalanced net force will result in an acceleration. So here's an example. This is an old test question, and we're just going to do a couple different things here. So we have a ring-shaped space station. It's rotating at a rate of 35 radians per second. Rockets on the station fire in slowest rotation to 12 radians per second in 32 seconds. If the radius of the space station is 40 meters and the space station has a mass of 30,000 kilograms, what is the magnitude of the angular acceleration of the space station? Okay, so we get a bunch of information here, and this is a multi-part question. So basically, this is your space station. It's a ring-shaped, and the idea is that people and stuff live in the little ring part of it, and it's got to be rotating in order to mimic gravity. And so what we're doing is we're slowing it down here. Maybe it's going too fast or whatever it might be. And so there's little rockets pushing out here and here to make this thing. So you're actually reducing the spin, so the angular acceleration would be in this direction here. So now let's think about this, and we'll talk about this one in a second. So what do you think is the angular acceleration? All right, this one we could have done a little while back, and so this answer is C, and basically it's taking one of our kinematic equations, this guy right here. So we know the initial and the final angular velocity, and we know the time. And so alpha is just going to equal omega final minus omega initial divided by the time. And when you plug that in, you get the 0.718 radians per second squared. So the next part of this multi-part question is to find the moment of inertia of the space station. So think about this one and see what you come up with. All right. Hopefully you got B. So this is one, the space station is a ring shape. All right, that's told us here. And so it's one of those ones you can look up in the book. And here it is. The ring shape is mr squared. So for a ring of mass m and a radius r, it's just mr squared. You plug those two numbers in and you get this here. 4.8 times 10 to the 7 kilogram meters squared. And finally, the part we're going to use some new information is what force does each rocket apply? So try this, and as a hint, I'll tell you that we're going to use our new equation here. So give this a try and see what you come up with. All right, now the thing about this one, so the answer I get is C, is that we just calculated the angular acceleration and just calculated I. So we know the right-hand side. And so the whole trick is finding the left-hand side. So now with a problem like this, that's a dynamic problem, there's usually going to be an axis of rotation that you have to pick. And here it's going to be the center of the space station. And so if I look here, the moment arm for our force is just going to be the radius of our space station. So for the torque, okay, the torque is going to be the force of the rocket times r. That's going to equal I alpha. Now the thing is there's going to be two of them because there's two rockets. And so altogether it'll be 2Fr equals I alpha. And when I solve for the force, I get I alpha divided by 2 times r. And when you do that, hopefully you can come up with 4.3 times 10 to the 5th. We'll do much more examples of this kind of stuff in class.